before we start the video. It's going to be a long video. I'm going to probably keep you over. Class is going to run over. But it's an extremely important video, one that you may even consider watching 2 times. A lot of stuff going to be going on here, a lot of important stuff. Let's go ahead and get it going. So the data that I want to use as illustration is one we've used before. And remember, X in this case was the ACT for the student, and the Y was the student's GPA. And a couple of things I went ahead and calculated were, first of all, I'll tell you what, let me make sure I've got the sound up. It's actually happened before where, yeah, okay, everything should be good. Yeah. So what I did is I go ahead and calculated 4 things that we're going to use. So the very first thing, here would be the sum of the x of i's. And that's just simply adding 18 plus 22 up to plus 32, get 125. The second line we get is we get the sum of the x of I squares, and that just means we we square each x term and sum, and of course for that we get 3241. The sum of the y sub i's is just like the sum of the x sub i's, except we use the y terms, or the y values, I should say. So we add 2.4 plus 2.2, so on and so forth. And then the last thing we do is we take a sum of the products of xi, yi. Now, you've already seen the theory behind some of this, nevertheless, the value that I get, you can barely see the 8, but it's 354.8. Now, guys, so far, we've seen a couple of ways to calculate B0 and B1. And one, of course, is, using least squares. Let me try just writing with my finger. And another thing is to calculate B1. And divide that by the covariance, well, the sum of x sub I minus x bar. And we also saw that we could calculate B0 by taking y bar minus B1 times x bar. Now, that's not, incredibly difficult to do. We just have to find the mean, do some differences, products, summations. So there's actually more to it. By the end of the day, well, by the end of this video, I should say, we're going to come up with a new way to calculate beta 0, beta 1 using matrices, which will pretty much, except for maybe test questions, will pretty much make this and least squares obsolete. It'll especially make it obsolete once we get into multiple regression. So there are certainly limitations on this with multiple regression. One of the motivations for to looking at finding B0, B1 using matrices. All right, so guys, we've seen before that, and this would have been back in one of the previous videos. When I talked about creating what we call normal equations. And eventually what we're going to do is we'll take this. This is, when we have beta 0, beta 1, so we have a, a one predictor model. We'll eventually make this more general for N or predictors or P predictors. I think we'll actually end up with P minus 1 predictors. But for right now, all we're looking at is just for beta 0, beta 1. Now, it's really easy to see with just a little bit of algebra. Now, in one of my undergraduate classes, I probably had to spend a couple hours on this. Why did that term become negative? Why did that term become positive? But we certainly don't have to do that here. Now you're going to see some repetition from previous videos, but I'm a firm believer when I get in teaching mode that repetition is important when we're doing things that are super duper duper important, okay? Now what we can do now is we can take this and implement matrices. And what we know about multiplying matrices by now, we should be able to see that we can take in some xi, some xi, some xi squared times beta 0, beta 1. Now I've done this in a previous video, but I think it's important that you step back, justify that this matrix representation follows from the previous page. Now, gang, if we were going to create this matrix, N for our GPA data was 5. We saw the sum of the x sub i's was 125. Same thing here. And here we have 3241. So we have B0, B1, and from the beginning of this video we saw that this was 13.8 and this is 354.8. I think that 354.8, that's what we had, right? Yeah. Sorry for jumping around on you. Now, obviously what we can do here, well, I don't know if it's obvious, but what we can do here is we can take B0, B1 will be equal to 5, 125, 125, 3241, inverse times 13.8 and 354.8. Guys, sorry for writing so slow, but again, it's got sticky on me and it's kind of harder to write. So, guys, what we can do here is we can jump into R. And what I want to do here is I want to create one matrix. I'm going to call this matrix A, and I'll call this we'll call this whatever matrix. I hate to call it B because typically we call this our B matrix. We'll call this A C. Okay, so ultimately we'll find B by taking the inverse of A times C. And if you think about it here, with the inverse here, the inverse of a square matrix is still the same size, so we're going to have 2 by 2. And here we have a 2 by 1. Center numbers are the same. So we're going to end up with a matrix, a 2 by 1, which is exactly what we need to solve for beta 0, beta 1. All right, let's jump over to R. I've already got it up here, and by now we should be able to easily create a matrix. So I'm going to use small a here for the entries. So I have 5, 125, 125, 32, 41. All right, and I'm going to call this, what we call a C, didn't we? So I'll call little c. And I'm going to go 13.8 and 354.8. All right. Next thing I'll do is set up my matrix A. And so I'll use the matrix command here. And I will use the entries from A, small a. And I'll have in row equal 2. In column equal 2. And by row equal true. Now guys, I'm not sure if you have to capitalize true there. Seems like to me for some reason, I've tried it before and you do. I'm not going to test it. You can test it, okay? So I'm just going to check and make sure if that's the matrix we truly need, and we do that. All right. Next thing I want to do is I want to create the matrix C. So I'm going to use the entry C, and I will have, 2 rows. In column equal 1. And I want it to read my my small c by row, okay? So again, let's just make sure it works out. So what we're going to do here is we're going to take the product, the inverse. Now, I have no problem with going ahead and just doing inverse A equal solve A. That's perfectly fine. You could type it all out. But nevertheless, guys, small b is going to be the product of inverse A. And remember, we have to do all this wacky stuff with to multiply matrices and times C. And we get B is the following values. Now, I'm going to write this down. So B0, I'm going to, before we go on, so 0.648. And beta 1, and we've seen these answers before. They're not like, it's not like it's a shock to us. Now we get 0.08. I'm going to go out 4 places on the. All right. So we have solved for the estimates of beta 0, beta 1. Now, what I want to do now is I want to go back, and you can see I've written these down because I'm certainly going to want to illustrate other ways of getting these values, which also give us some important results. So, guys, let's just look in general. So in general, we know we have our model y sub I is beta 0 plus beta 1, x sub I plus the error term. So I can look at some matrices from this. First of all, I can look at my Y matrix. And I'll call this the response vector. And next thing I'll look at is x equal, guys, don't forget the 1s here. I'll show you why they come from. And I refer to this as the design matrix. All right. I'm going to create one more well, I'll tell you what, let's do this. Technically, we've still got beta 0, 1. So this would be our coefficient. Vector. And of course, we're going to have our error term. And this is our error vector. Okay, now if we put x and b together from what we know about multiplying matrices, let's go back here. If we multiply x and b, what we're going to do is we're going to take a linear combination of the first row and the first column in b, so we'll get beta 0 times 1 plus beta 1 x1. And of course beta 0 plus beta 1 x2. And finally we'll get our last term. Beta 0 plus beta 1 xn. And put the dots in there because we got more terms clearly. So guys, ultimately what we get there again is we get y equals x beta plus the errors. Now something to remember is our expected value of the error terms is going to be equal to 0. So boys and girls, we can say that the expected value of E1, the expected value of E2, and the expected value of En will be equal to zeros. All right, now we're getting ready to get into some drum roll, please. Okay, so guys, I don't want to over dramatize this, but I'm going to. This is important. So somewhere in your notes, you're probably, I don't know what minute, second we're at right here, but you might want to say video 30, 20 minutes and 18 seconds, whatever it may be. Now, guys, from previously, the way that we came up with the estimates of beta 0, beta 1 so far was, of course, solving this. Easy to say, tough to write. Now, just curious, does anyone remember what we called that matrix right there? Well, I went back and found it, and we actually found that the product of x transpose times x gives us this. In fact, guys, if you'll go back to video 28, we did this at about the 5624 mark. Now, we also saw on that same video, video 28, and I went back and even looked at it, and this was at the 54. Now, you got to admit, this is service. You guys should tip me. All right. So at 5405, we saw that this matrix was x transpose times the y vector, times the response vector. So guys, long story short, what we end up with here is we end up with x transpose x times b equals x transpose y. Guys, I'm going to multiply both sides by x transpose x, and you're going to see something in, I think in video number 29, I told you that this product, the inverse, is going to play an important role. Well, here it is. So we'll take that times x transpose x beta. And guys, we multiplied by the left side by the inverse, so we got to multiply by the left side over here. We don't have the luxury with matrices that we have with real numbers, and that they're commutative. In general, matrices aren't commutative, so if we multiply one side on the left side, we have to multiply the other side, left side. Now guys, the reason I multiplied by the inverse here, and it may be better to see it like this, is because that gives me the what essentially gives me value of 1. So what I end up with here is I end up with B is x transpose x inverse x transpose y. Now the beauty of this is we have B in terms of our essentially our response vector and our design matrix. Now granted, we take the transpose, granted we take the inverse, but nevertheless we don't have to sum up our x's, we don't have to sum up our y's, we don't have to take the product, and we get this. Now this is under an FYI, and I can almost guarantee you on your one of your exams you're going to be expected to demonstrate this. Where does this come from? How do we tie everything back together in terms of this being the minimum distance, the sum of the minimum distances squared when we looked at the least squares approach? So guys, you know, put some flashing neon lights, star, whatever around this. You know, this is big time stuff. So what we need to do first of all is, let's see again that we have y equal x beta plus our error term, and we can clearly solve this for E by going y minus x times beta. Now to get our error squared, we have either got to investigate error transpose times E or errors times error transpose. Now if you examine this one right here, error transpose is going to be a 1 by n row vector, and our errors is going to be an n by 1 column vector. These are the same, resulting in a 1 by 1 vector, which essentially is the sum of the error squared. This vector, although it's cool, okay, this is an n by 1, 1 by n. It's a cool vector, 1, 1, but we would get an n by n vector, which doesn't get us what we want when we're summing up the error squared. So guys, we're going to focus on this one right here, and we're ultimately going to want to be able to minimize the sum, which is to minimize the sum of the error squared. So essentially guys, when we have E equals y minus xb, we're going to multiply this side times its transpose, which means we're going to have to multiply this side times its transpose. Hey, you're okay. Don't worry about it. So in terms of minimizing the sum of these distances, what we've ultimately got to focus on is we've got to focus on how we're going to minimize the product of y minus xb transpose times y minus xb. Now think it through. What what do we do to find the minimum value here? Well, we're going to take ultimately take the derivative, set it equal to 0, and solve, okay? But first thing I want to do here is I'm going to say that I'm going to let Q, as the notation we've used before, be the value on the right side. And go is to minimize Q with respect to some form of beta. Now we'll probably end up, I don't remember exactly what happens here, but we may end up differentiating with respect to beta transpose, but we'll just have to examine what we end up getting. So guys, let's multiply this out. Now again, in multiplying y minus x b transpose times y minus x beta, we have to pay attention to order. So this, using FOIL, did you ever think you'd use FOIL in a graduate level math class? Anyway, you're going to. So here we have y transpose. We have to put it first because it's from the left. Now the next thing we get is we get this. Times y. And next thing we get is we get y transpose x b. And we will get plus, let's see, we're going to get so we'll get x beta transpose x beta. All right. Now there's a important property about transpose that says if we have A, B transpose, this can be rewritten as A transpose B trans. No, it can't either. I just lied. First mistake ever, boys and girls. B transpose A transpose. So check that out sometime. Trust me, it's true. But think that out and see why that's the case, and see why it's not what you would think it'd be. Would be A transpose B transpose. So what we're going to end up with here is we're going to have y transpose y, and this allows us to look at the next term. And same argument here. We're going to get B transpose X transpose X and beta. Now, okay. I don't know what to do next. All right, let's examine this right here. Let's examine this y transpose x. So technically it's minus, but I don't care about that right now. I just want to examine this, and that is the way it came to us, right? Yeah. Now, the y transpose, our y is going to be in n by 1 vector, so the transpose is going to be a 1 by n vector. X is going to be a n by 2. And the beta matrix is going to be a 2 by 1. Now let's examine this part right here. The product here was going to be a 1 by 2. Bringing this down, we get a 2 by 1. So ultimately, guys, what we get here is a 1 by 1 vector. No, it's 1 by 1 vector. It's 1 by 1 matrix. Now there's a rule, and I'm not going to write this down, but there's a rule that says if we have a 1 by 1 matrix, that this matrix, let's just let it be some generic A, that the matrix A will be equal to its transpose if it's a 1 by 1. Seems like it's yes. Okay, good. So we clearly have a 1 by 1, and if you think about, now go up here and think about the transpose here, well, remember we just reverse everything and give things that don't have a transpose, and things that do have a transpose, not a transpose. Did you get that? And we're going to end up with this. So that essentially is going to take the place of this term right here. So let's scoot on over here. So now we're going to have y transpose y minus beta transpose x transpose y minus, now we're going to go back over here and get what we got from all this work on this page. So it's beta transpose x transpose y. And then in the end, we're going to have plus, and just to remind you, this is just nothing more than this term right here. So beta transpose x transpose. X transpose is the direction, xb. Guys, in matrices, we don't have the luxuries of, 2 times 4 being 4 times 2. We have to be concerned with order. So guys, you can probably now see what all the fuss was about. These two center terms now become the same, so we can add those, get -2. And get this. Now, the next thing I want to do is I want to take the partial of q with respect to beta. But if you notice, I don't have a beta term anywhere but here. So it's actually going to be to my advantage to take the partial with respect to the beta transpose. And when I do that, this term here doesn't have a beta transpose, so that goes away. This term right here with respect to beta transpose will of course be -2 x transpose y. And this term right here is going to be with respect to beta transpose, we have x transpose, well, that may be the ugliest t in the history of t's. X transpose x beta. Works out nicely because we want to ultimately solve for beta. Next thing we want to do, as you would have hopefully know by now, set this equal to 0 and solve for beta. So guys, setting it equal to 0, we're going to get x transpose x. That's what I thought. All right, clearly. So if we multiply both sides by x transpose x inverse x transpose y, x transpose x inverse x transpose x beta, we get cool things happen right there, which at the end of the day says that our beta can be found by taking so all we got to do is be able to calculate our uh, well, I mean, essentially what we got to do is be able to find our x and y matrices. Well, guys, it turns out that's super easy to do. So x is going to be and y is going to be this. All right, let's get out of this, and guys, remember again, we're expecting. Again, we're not reinventing the wheel here. Remember that for beta 0, we got shoot. Did I write that down somewhere? Probably not. I'm not that clever. I'll tell you what. Let me check here. I may have written that down somewhere. Yeah, this was 0.648, and beta 1 was 0.0845. All right, gang, let's see how it happens. Let's go into R. You can easily do this in your graphing calculator. It'll be something I'll show you when we go face to face, probably even before you watch this video. So the first matrix I need is, I'll tell you what I'm going to do. I'm going to close R down. I want to get rid of all this stuff. I don't want anything stored. I don't think it would matter, but don't want to take the chance. All right, so let's open it back up. Maybe. All right. So guys, let's go ahead and do our X matrix, and there are other ways, and feel free to. I'll tell you what I want to do. I want to do this. I want to show something that I demonstrated in an earlier. I want to do my ACTs as 18, 22, 25, 28, 32. What did I do wrong? Oh, I see. So 18, 22, 25, 28, 32. And this will happen a lot where we've got our X of i's in maybe a CSV file or a Excel file, whatever it may be, and we'll need to bind these things together and get ones. And so I want to show you how to do that. Let's go ahead and do our GPAs. Should have this memorized, but I don't care enough to memorize it. It's just numbers. And just for illustration. All right. Now, first thing I want to do is I want to create my X matrix, but what I need to do there is I'm going to have something I need to add to it. So I'm just going to very cleverly call this add. And really what I want is 5 ones. Okay. I tell you what I'm going to do. I'm going to call this there's like 3 different ways I could do this, but I think what I want to do first is I want to create a matrix from ACTs. And I want in row equal 5, in column equal 1, and by row equal true. And the reason I'm doing this is I want to show you that matrix A isn't yet what we want it to be because we have to put the 1s in front. So I want to call this matrix X now. And what I need to do is I need to go C bind A, but I need to put the 1s first, don't I? So add A. And now you can see I've got the matrix that I need. Clearly, we could have gone up here in the beginning. Instead of looking at ACT, we could have gone, 1,18, 1, 18, 1, 22, 1, 25, and had everything we need. The reason I want to do it this way is because there's so many times we're going to have our X values, and we're going to need to bind the 1s as I just did. All right, gang, let's go ahead and create our Y matrix. So Y is going to be matrix for GPA, and clearly we want 5 rows, in columns equal 1, by row equal true. So guys, your Y matrix is going to be this. Now let's think what we need. We're going to need X transpose. So let's go ahead and get it. So I'm going to call that X transpose. And remember, to get that, we just go transpose X. So we can now look at that vector, or I'm sorry, that matrix. And we're going to need the inverse. But we'll go ahead and take care of that when we're solving for beta. So I'm going to call this beta. Now, how do we do the inverse? Well, we do solve, and then we're going to go X transpose. And guys, again, remember, to multiply matrices, we have to do this. And then I'm going to, let me see, X transpose X, so solve gives me the inverse. Okay, that's cool. Now what I need to do is I need to multiply this times X transpose. And then I need to multiply this times Y. And when I do all that correctly, you can see that I get my betas much more efficiently than we've ever done it before. The only thing we've got to be able to do is take our data, put it in what we call our design matrix, take our response vector, which is our Y values. And, obviously, guys, you should be able to appreciate where we're headed with this when we have multiple predictors. This is going to be super, super easy. Instead of finding some xi's, and you got to think about it. If we have multiple predictors, we have more than one x. So the summations, when you do it longhand like that, get kind of crazy. Now, let's go back and look at a little bit of theory. Everybody's favorite part, right? So one thing you'll notice is that X times beta is our expected values. And we've been speaking that lingo for a long time. So it follows that our expected values of our y sub i's is equal to beta 0 plus beta 1 x sub I. So, all right, so as a direct response from this, gosh, what did we want to do here? You know what? Let me see. I've got a lot left to do. And we're 46 minutes. You know what I'm going to do here? I'm going to end this video. So this is going to be the end of video 30.